Here we are asked to look for the distribution. Well, a distribution is called symmetric unimodal if it's symmetric about some point and has a unique mode. And here we're given that the normal distribution is symmetric in unimodal. And we are asked in this exercise to find the mean, median, and mode of x, when x is defined as a continuous symmetric unimodal distribution for which the mean exists. Okay, so let's start by giving the definitions of the mean, median, and mode. And the mean of x, and this is now a continuous random variable, so over its support we define the mean in the following way, and let's just call this mu. The median of x, let's put that, set that to m. That is defined as the probability of x being larger or equal to m with a probability of half, larger than half, and simultaneously also x less than m is also probability half. So these need to be true simultaneously, and basically this means that for a distribution, let's call this, let's just show this as the normal, something like this, we'll have half the distribution to the left of m and the other half to the right of m. And this means that the distribution here is a half, and the other distribution here, the density mass function, is also a half. So this is what the median intuitively means. The mode is the most typical value of a random variable. Let's call that c, and that is defined as the density being larger or equal to all other values, for all other values x in the support of the random variable x. And this basically has the meaning that the density of the mode is at least as large as all other densities of x. So basically it's taken up at least as much density as x for each x, or more of it. So it's the typical value basically of that random variable. Okay, so these were some definitions, and we're also given information about that x is symmetrical about u. Well, so what does symmetry mean? Mu, I just said, is the mean here, but symmetry basically means that x is symmetric about a value that I just called mu, but it will actually coincide with the mean, okay, if it's symmetric. So we say that x is symmetric about mu if x minus this value has the same distribution as mu minus x. Okay, so basically whatever happens to the left and right of this point has the same shape. Okay, and now we're going to show that mu must be, it's a little unfortunate to use the same note here. Let me just do mu1 here, just to make this different from this mu that we are supposed to show. Okay, so we're not assuming it to be the mean to begin with. So okay, so must be the expectation of x. So it has to be actually the mu I just mentioned earlier. So how do we show that? So let's start by saying that the expectation of x minus this value, if we subtract that off, start there, that's just the same by, because mu 1 is a constant, we can just pull it in, and then now, because we just assumed symmetry, here we have symmetry, by symmetry we can now replace x minus mu1 with mu1 minus x. That's what symmetry means. So we can do this, and then that by linearity we can do the following. And so we've shown that these two has to be equivalent. And now sorry, if we focus on this term and that term, we can see, well, let me just copy it like this, and I'll copy that one like that. And now, by just simple algebra, by pulling up, pushing this term to the other side and that term to the other side, to the right hand side, we get 1, and the 2's cancel, and we have shown that expectation of x must be mu1, which is what we assume to be mu up there. Okay, so we've shown that the mean must be, for a symmetrical random variable, that constant has to be the mean. Let's now show the median. So let me just write, this was mean, median. All right, so the probability of x minus mu, assume it to be less than or equal to 0. Now again, by symmetry, that has to be mu, the following term, mu minus x, has to be less than 0. Now, well, unfortunately I used the term mu here again. We could have stick to m, but let's just stick to mu here for the sake of argument, and that will not do any harm moving forward. So this is now equal to, by pushing the mu's here to the right hand side of the inequality, we get probability of x less than or equal to mu, and the same here, we get u less than or equal to x. Okay, so I'll call this identity 1 because we'll be using it at least 2 times in the derivations. And looking at the this term here. Let's work with this one and see what we can do with it here in terms of showing how it reduces to the median. So this term has to be, well, this is the same as 1 minus the probability of the event being larger than x has to be larger than mu, and it's strictly larger because we said it's up to mu. Here it's mu and above. This is larger or equal to the same expression, or almost the same expression, but now including mu. Why is that true? Because when we subtract off, well, this is a continuous random variable, but think of it, if you add a little bit more density and you subtract it off 1, this term has to be less than when you don't include this little extra portion of the density. Okay, and that now is by identity 1, the same as 1 minus the probability of x less than equal to mu. All right, and that, if we now copy these terms here, this one and that one, and we know, we just said that the left hand side is larger than the right hand side, we then push the right hand side term, this probability, to the other side. We get 2 of it, like so, and that must be now larger than a half. Right, we divide by 2 on both sides, and here by identity 1 again, by this identity, we can replace this with that, basically flipping the inequality. And so we divide by 1, we also have that b a probability of x larger than mu has to also be larger than a half, and these together fulfill the definition of the median for mu. So mu has to be the median as well. Okay, so we have now done the mean and the median. Let's move on to the last part of the question, which is that we also asked to show that the mode is equal to the same value. Okay, so let's start with setting assume mu, again the mean, assume it to that the mode is mu plus c, and this is the unique value of for the mode of x. But so this is step 1. Step 2 is that by symmetry we have that c minus mu is also a mode. Okay, but we just assumed that the mode is unique. So that it means that mu plus c and c minus mu has to be equal. Now what does that show? Well, that shows that c is 0 and mu is equal to c. Yeah. So it means that the mode and the mean and the median are is mu. Okay. So now going back to the question, we have shown that the mean, the median, and the mode are all equal.